take a look at a couple more transformations together and then give you an opportunity to practice some of those. So let's take as our parent function f of x equals 3 to the x. So my base is 3, so that's bigger than 1. So this is going to be another exponential growth. Y-intercept of 0, 1. And I can very quickly plot the point 1, 3. And the point 1, sorry, negative 1, 1/3. And that helps me get the right growth rate. Okay, what I'd like to do first is take a look at g of x equaling 3 to the 2x, so that I'm doubling x, doubling the exponent before I plug things in. So if I take a look at how I would evaluate that, I would multiply by 2, and then I would take the power. So I would raise 3 to that exponent. That's my parent function. So the corresponding transformation, since I'm doing that before the parent function, this would be a horizontal transformation. Okay. Multiplying x by 2 makes it bigger. Remember that horizontal transformations are counterintuitive, so this is going to be a horizontal shrink by a factor of 1/2. Okay, so if I were to sketch that, let me just sketch that here. Okay. My y values are going to stay the same. The x values, I'm going to do the opposite of multiplying by 2. I'm going to divide by 2. Okay. So this x value, instead of being at negative 1, it's now going to be at negative 1/2. So I would have negative 1/2, 1/3. Okay. 0, 1 is going to stay at 0, 1. Okay. And now this point, instead of being at 1, 3, is going to be at 1/2, 3. Okay, so with a shape like this, it's a little bit hard to see that we've done a horizontal shrinking, but we have. I want to just point out something, though, that's kind of interesting. You don't actually see any of these horizontal shrinkings or stretchings in the homework, and there's a reason for that. That's because this is equivalent to 3 squared to the x. This is the same as just 9 to the x. I could just as easily have rewritten this and said this is, instead of transforming the exponential function 3 to the x, this is just the exponential function with a base of 9. Okay. Now, if I take a look, 9 to the 1/2, remember the 1/2 power is the square root. Square root of 9 is in fact 3. Okay. If I were to plug in 1, obviously 9 to the 1st would be 1. If I plug it in here, would be 9. If I plug it in here, 2 times 1 is 2. 3 squared is 9. Okay. So if I view it as a transformation of the graph with base 3, I'm going to be plotting different points than if I view it as just the parent exponential function with base 9. But we really don't need to concern ourselves with horizontal stretchings and shrinkings because those can be accomplished more simply by just using a different base. Okay. All right. Now, I want to look at also what happens if we multiply by a negative number. Now, you will see some of those, but that could also be accomplished by just changing the base. So let's look at h of x equals 3 to the negative x. Okay. So here, in evaluating this, I would first of all multiply by a negative 1, and then I would raise 3 to that power. So as far as my transformations goes, raising 3 to that power, that's my parent function. So this is, again, a horizontal transformation. Okay. And this is going to be a horizontal flip. So we're changing our x values. I need to do the opposite of multiplying by negative 1, which would be dividing by negative 1, which it turns out is exactly the same as multiplying by negative 1. So this, instead of being negative 1, 1/3, we'll have a point at 1, 1/3. 0, 1, we'll still be at 0, 1. And instead of being at 1, 3, we'll be at negative 1, 3. Now that's very interesting. When I reflect the graph horizontally, it goes from being exponential growth to being exponential decay. Oops, this was the point negative 1, 3. Okay. Well, I can do something very similar here to what I did in the previous example. I can say this is 3 to the negative 1 times x, which is the same as 3 to the negative 1 to the x. We're more used to seeing the rule this way. When I have a power to a power, that's equivalent to multiplying the powers. But if I'm multiplying powers, I can say that's a power to a power. But this is just the same as 1/3 to the x. Okay. So you will see some examples in the homework that do have a negative sign up there in the exponent so that you are viewing that as a horizontal flip. But a horizontal flip does the same thing as just changing the base to the reciprocal base, which I think is kind of interesting. Okay, excellent. So I wanted to just point that out to you. All of the transformations that you're going to see in the homework involve just shifts and flips. Okay, so you're not going to see any stretching and shrinking. Now, for the horizontal stretching and shrinking, I showed you that we could accomplish those just as easily by changing the base. I'm honestly not quite sure why the book doesn't do vertical stretches and shrinks, but we will see those when we get to the applications. Because in applications, we're not always going to want to have a y-intercept at 1, even if we want the horizontal asymptote to be at a height of 0. And so we will then see in our applications that we're sometimes multiplying an exponential function by a number. But in the homework, you're really going to be just focusing on shifts and flips. So I want to let you practice on one of them. So this is number 33 from the homework. It is an assigned homework problem. So again, working through this video, you're getting a jump start on the homework. Okay. Now, what you're asked to do is use transformations to graph a function. So I'm going to modify the directions a little bit. Let's just graph the parent function. In this case, is going to be y equals 1/3 to the x. And for that, I do want you to include the points whose x values are -1, 0, and 1. Pretty much you can expect anytime I'm asking you to graph an exponential function, I'm going to ask you to include those 3 points. So you might as well just get used to it. That's the level of detail I'm looking for. Okay. And then you're going to be graphing y equals 1/3 to the x plus 1 minus 3. And I will want you to track those points. So if there are horizontal transformations, your x values will change, but I want to see what they change to. Okay. So that's your basic graphing. Now I also want to include the directions that are given in your textbook. So once you've graphed it, state the domain and state the range. Give both of those in interval notation. And anytime you have an exponential function, you're going to have a horizontal asymptote. Give me the equation of the horizontal asymptote. So as you're doing the transformation, you're tracking these 3 points and the asymptote, and then the book's just asking to explicitly state where did that asymptote end up. So you'll show it in your graph, and then you'll also write the equation. All right, so give that a shot, and then we'll start the next video going over that together.